Jai Hind everyone. So this is the first lecture of computer networks that is related to BTech CSE third year. It's coded BCS 603. It is from unit 1, that is physical layer, data and signal. So data, the data that is transmitted through communication channel that can be analog or digital. In computer network, we are transmitting our data through various types of computer channel, communication channel. The communication channel can be guided or unguided media. So on that communication channel, the data can be transferred in the analog form or digital form. The term analog data refers to the information that is continuous in nature, while the digital data refers to the information that has discrete states. And the analog data takes on continuous values and digital data takes discrete value. So the various topics discussed in this section is analog and digital data, analog and digital signals, and periodic and non-periodic signals. So the data can be analog or digital in nature. Analog data are continuous and take continuous values, while digital data have discrete states and take discrete values. Signal can be analog signal. Analog signal can have infinite number of values in range. Like for example, its range starts from 1 to 100, while in digital signal can have only a limited number of values. Like for example, if I am saying that 100 kbps, 10 mbps, but in analog, its range, it is range fluctuating. So this is the comparison of analog and digital signal. This is a diagram of analog signal that its range is fluctuating in this way, while in discrete signal, it is discrete in nature. The shape is fixed, that is somehow it is fixed, it is also fixed, it is fixed. So this is the basic difference between analog and digital signal. In data communication, we commonly use periodic signals, analog signals, periodic analog signals, and non-periodic digital signals. So what is periodic and non-periodic signals? In periodic analog signals, it can be classified as a simple or composite. A simple periodic analog signal, a sine wave that cannot be decomposed into a simpler signal. A composite signal, analog signal, is composed of multiple sine waves. So if we take about the signal with a high peak amplitude, so this is the high peak value of an analog signal. This is the high peak. So high peak, it means it measures the amplitude of the signals, while if we talk about the signal with low peak values, it means the signal do not have the high peak values, high peak amplitude. So this is the peak amplitude. So this is low signal and this is high peak signals. The frequency can be defined as a and period are inverse of each other, that frequency f is equals to 1 upon t, or you can say that t is equals to 1 upon f also. So the two signals with the same amplitude and phase but different frequencies. So the first one is a signal with a frequency of 12 hertz, second a signal with a frequency of 6 hertz. You can see that its frequency, the peak value is almost similar. It's similar, but in a limited amount of time, it can travel a various signals in this. While in this, it can transfer a limited amount of signal. So the period can be defined as 1 upon 12s. It means the 12 different types of 12 signals can be delivered in 1 second. In this, only 6 signals, 1, 2, 3, 4, 5, 6. So 6 signals can be delivered in this in 1 second. So here in this diagram, 12 period in 1 second, the frequency is 12 hertz, while in this diagram, 6 period in 1 second, so frequency is 6 hertz. So basically, this you can relate the units of period of and frequency. If the unit is a second, 1 second, and in hertz, we can say it is 1 hertz. If it is 10 to the power minus 3 second in kilohertz, we can measure is 10 to the power 3 hertz. In unit, it is 10 to the minus 6 second. In megahertz, you can be called at 10 to the power 6 hertz, and so on. So the example, the power we use at home has a frequency of 60 Hertz and the period of sine wave can be determined as 1 upon f 1 upon 60. It means 0.0166 second, or you can say multiplied by 10 to the power 3 millisecond, 16.6 millisecond. Another example, the period of 100 millisecond in a microsecond. So from the table, we can say that 100 millisecond is equal to 100 into 10 to the power minus 3 second. So we can say that if we are converting this 100 millisecond, so we can get 10 to the power 2 multiply 10 to the minus 3 multiply 10 to the power 6 is equal to 10 to the power 5 microseconds. So this you can convert in this way. Okay. So frequency is the rate of change with respect to time. Change in a short span of time means high frequency. Change over a long span of time means low frequency. So if a signal does not change at all, its frequency is almost zero. If a signal changes simultaneously, it means its frequency is infinite. The phase describes the position of a waveform that is related to time 0. So we can see that 3 sine waves with the same amplitude and frequency but different phases. The first one has 0 degree. The second one has 1 upon 4 time phase. Another is 1 upon 2, because a complete signal can be measured from this point to this point, one up and one lower. So here the start point is 0, it means the signal start from here, but in this diagram the signal start from here, and then in this diagram the signal start from here. So it means it says 0 degree, it's 90 degree because it covers the 1/4 signal and it covers 1/2 signal, so it means 180 degree. So a sine wave is offset 1 upon 6 cycle with respect to time 0. And what is its phase in degree and radians? We know that one complete cycle is 360 degree, one complete. So half cycle is 180 degree. So therefore 1 upon 6 cycle is 1 upon 6 into 360. So that gives 60 degree, or you can say 60 multiplied by 2 pi upon 360 radian. We can say that 1.046 radian. Okay. So wavelength and period. So this is a wavelength. It means the signal start from this and end from this. This is a wavelength, and this is a transmission medium. Through a transmission medium at a time, we can say that this particular signal can be delivered through this channel and this ways. So the time domain and frequency domain plots of sine waves. So in this diagram, we can say that the peak value is 5 volt. The peak value 5 volt. A sine wave in the time domain frequency 6 Hertz. It means 1, 2, 3, 4, 5, 6. 6 signals is transferred in 1 second. So we can say that if we draw the same diagram, the diagram in this form, so 6 signal is transferred in a single second with a peak value of 5 volt. So this can be converted into this diagram also. So this figure. Now we have discussed about the simple signals. So this is a diagram of composite signal, composite periodic signal. Like for example, if we are talking this signal, so this is a simple signal and this is a composite signal. Means what? At a peak value, if we observe this peak value, the signal can be transferred in this shape also, at the lower bound also in this shape. So this is a composite signal. This particular diagram represents that this type of signals is a composite periodic signals. So this decomposition of a composite periodic signal in the time and frequency domain, like for example, in this, we can treat this is also a type of signal. This is another. Like for example, if we discuss particular this peak and the lower, so we can calculate, we can assume that this is also a type of signal. So this is. So we can take the example, we can take this particular signal for further discussion. So this is a decomposition. So in this decomposition, like for example, this is a frequency f. In blue shape, this is the frequency 3f. The black one is the frequency of 9f. And in the similar, we can show this particular frequency in the second diagram in composite signal. This is f, this one, this is 3f, and this is 9f. Okay. So this is the diagram. Next figure show the non-periodic composite signal. It can be signal created by a microphone or a telephone set when a word or two is pronounced. In this case, the composite signal cannot be period, because that implies that we are repeating the same word or words with exactly the same tone. So that's why. So this is a time domain and this is a frequency domain. So this is the time and frequency domain of a non-periodic signal. Okay. So the bandwidth of a composite signal is the difference between the highest and the lowest frequency contained in that signal. So this is very important concept that we will discuss later on. So what is this? The bandwidth of periodic and non-periodic composite signal. Like for example, if the bandwidth starts from 1000 and the bandwidth is 5000 and set. So the exact bandwidth is 5000 minus 1000, that is 4000 hertz. This is the bandwidth. This is the periodic signal, and the below diagram is an example of non-periodic signal. But in non-periodic signal, the bandwidth is again 4000 because it starts from 1000 and ends at 5000. So 5000 minus 1000 is equals to 4000 hertz. So we take another example to calculate the bandwidth. So in this example, if a periodic signal decomposed into various 5 different sine waves with the different frequencies, 100, 300, 500, 700, 900 hertz. So the highest frequency is 900 and the lowest frequency is 100. So what is its bandwidth? 900 minus 100, that is 800 hertz. This is the frequency. Okay. So this is how you can calculate the frequency, highest minus lowest. So you can calculate the bandwidth. And you can draw the diagram of the same 100 to 900. The voltage, the frequency is remain constant. This is same. But what is the bandwidth? 900 minus 100, that is 800 hertz. Okay. So in this example also, there are two different type of periodic signals, that is 20 kilohertz and 60 hertz, 20 hertz and 60 hertz. So in this case also, if we are calculating the bandwidth, so highest frequency minus lowest frequency, that gives 60 minus 20 hertz, that gives 40 hertz. And this is the diagram. 60 minus 40, that is 20 hertz. Start from 40 and ends at 60. 60 minus 40, that is 20 hertz. Okay. So this we can skip. Now digital signals. We have discussed the various parameter of analog signals. Now comes on digital signal. So in addition to being represented by an analog signal, information can also be represented by a digital signal. For example, 0 and 1, that can be represented in a computer. In a computer, 1 is represented as a 1, means high. It means it is positive, while 0 is represented as a lower, or you can say it is negative. A digital signal can have more than 2 levels. The levels can be different. Like we have 3 levels that can transfer the 1. The 1, 1, 1, there are 3 levels we can transfer, though there can be more than 2 levels also. In this case, we can send more than 1 bit at each level. This is the beauty of this digital signal. Yes. So these are the 2 signals. This is signals and these are the different levels. If we see, this is a very simple diagram that all students have seen this diagram, that this is 0 and this is 1, this is 1, 1, 0, 0, 0, 1. So this very simple diagram, we can all understand that what this signal is. This is a simple 2 level. The level 1 represented as a 0 and level 2 represented as a 1. While the another diagram in this, it has different levels, because the lowest one is treated as a 1, the second lowest is treated as a level 2, the next one is treated as a level 3, and next one is treated as a level 4. So it means We have different levels while transmitting our digital signal from one end to another end. So if we are saying that this is 1 1, this is 1 0, this is 0 1 0 1 0 0 0 0 0 0 1 0, what is represents for? Like for example 1 1, it means this is level 4, it means it is a third signal. 0 to 4, it is fourth signal. So this is 0 1 2 3, so that's why it is represented as a 1 1. 1 0 2, 0 1 2, so that's why it is represented as a 1 0. Okay, so a digital signal has 8 levels. How many bits are needed per level? We can calculate the number of bits from the given formula. The formula is number of bits per level is log 2 and the 8 is the 8 levels. It means log 2 2 to the power 3, which gives 3 log 2 2, which gives 3 multiplied by log 2 base 2 is 1, it gives 3. So it means there are how many number of bits per number of bits can be transferred? 3. Okay, so this is how we can calculate this. Next, yes, assume we need to download a text document at a rate of 100 pages per minute. What is the required bit rate of this channel? So we should understand this type of examples also. 100 pages per minute. So you need to understand a one page consists of how many bits or bytes information. In a computer system, we can say that there are 80 columns, there are 80 columns and 24 rows are there in a computer screen, or we can say in a page. On a page, there are 24 rows and 80 columns are there. So that's why 24 rows and 80 columns. So it means we are calculating the number of bytes that one page can have, and each byte is of 8-bit long. So we have to multiply it by 8 also, and there are 100 pages, so we have to multiply it by 100. So that's why this is a full information that 100 pages and each page contain 24 rows and 80 columns, and each cell is of 8-bit size. So we have to calculate multiplied by 8. So it means this BPS bits per second, or you can say 1.636 Mbps. This we can calculate in this way. So next, what is the bit rate of high definition TV, HD TV? HD TV, it means the bit rate. In the similar way that we have calculated the 100 page per minute. So in this way also we have to assume, we have to identify about HDTV resolution. The HDTV resolution is 1920 by 1080. Okay, and you know that in a given movie, 1 second, it has 30 frames per second. 30 frames per second. They are reflecting 30 frames, 30 images in a second. Then only the video will be played. So 30 images 30 times per second, it refresh rate. जितना refresh rate अच्छा होगा, उतनी quality अच्छी होगी. It means 30. If your computer, if your TV screen gives a 60 refresh rate, it means 60 images, 60 frames per second. The quality is much quite higher. So let's say 30 times per second. So 1920 multiplied by 1080 multiplied by 30 multiplied by 24. What is this 24? The color pixel. In an image, if we are checking that image color intensity. If we are talking that the particular image is 32-bit representation or 24-bit representation, 16-bit representation or 8-bit representation, but it is HD TV, so we can say that there can be a 24 bits per pixel, 24 bits. One color can be represented by 24 pixels, 24 bits. Okay, so that's why we are converted into 24. It means 1920 into 1080, this is the total number of pixels, and each pixel can have 24 bits data size, and 30 is the refresh rate or 30 frames per second. So this we can say that 1.5 Gbps. So it means for HDTV, the bit rate is 1.5 gigabits per second. So this is the that's why we can say that on a broadband channel only, on a high speed network only, we can play the HDTV. Okay. So baseband transmission, or you can say broadband transmission. So baseband transmission, it means through a channel we can deliver a limited amount of data that can be delivered from one end to another end. That is called baseband transmission. A digital signal composite analog signal with an infinite bandwidth also. So bandwidth of two low pass channel with wide bandwidth and low pass channel with narrow bandwidth. If we are talking about the wide bandwidth, it means this is the wide bandwidth and this is the narrow bandwidth. The baseband transmission using a dedicated medium, it means input signal is this, input signal bandwidth, this is a supported by medium, particular medium is given to pass the particular data from one end to another end. This is the output signal. When this particular data is passed through a medium, this is the receiving signal. The shape of the signal can disturbed. You can see that this signal is converted into this one, and this particular signal is converted into this one. So this is a signal, this is a noise, or we can say after passing some distance, the signal can lost its energy, the signal can lost its shape also. So baseband transmission of a digital signal that preserve the shape of the digital signal is possibly only if we have low pass with an infinite and very high bandwidth only. Otherwise, its shape can be changed. Okay. So in baseband transmission, the required bandwidth is proportional to the bit rate. If we need to send bit faster, we need more bandwidth. Okay. So next one is yes, transmission impairment. So this all about the signals, analog signal and digital signal. How the data is transmitted through the various types of communication channel. Like for example, if I am saying that through this air medium, this is a spectrum, and in this spectrum my voice is recorded to this mic, my voice is listening to you also. This particular spectrum, this particular air medium can also have the signals of some Wi-Fi, the signals of mobile signals, the signal of various you can say that dish antenna signals. There are various types of signals are already floating in this air signal, this medium, and this is the radio signals. These are the radio signals. The radio signals are traveled nearer to Earth. So in this air spectrum, we have the radio signal in the form of either the Bluetooth devices, either the Wi-Fi router or switch is there, either I am talking to you. So all are the radio signal, you can say, in the form of energy. Okay. So yes, one question in your mind that if we are communicating with Bluetooth, so what is the type of signal? It is also radio signal. If this one is straight through, if I am directing to you by this remote like in TV, so this has infrared. But in infrared signals, we have some obstacle in front of this, so the signal cannot pass through this obstacle. So we have radio signal instead of this. So these are the different types of signals. Now what happen if we are transferring these different types of signals through this medium? The medium can be wired or wireless. But what about the noise? Can you imagine that noise play a very important role? Noise can be beneficial to us as well as noise can be, we have to discard, we have to clear the noise also. So we have to understand what type of noise is beneficial to us, what type of noise we can discard. Okay. So this particular section, transmission impairment, we can understand that what type of different type of noises are there, which type of noise which type of noise we can disturb the shape, which type of noise we can change the signal. We are transmitting this thing and you are receiving another thing. So signal travels through any transmission media, wired or wireless, that cannot be perfect in any manner, that cannot be perfect. You have already seen that, already seen in this, yes, this is in baseband also, wide baseband channel, the signal shape has been changed. So the change of signal is very common in nature. The noise inclusion with the signal is very common in nature. We have to take some precautions to avoid this particular type of things that can change your signal, that can change the shape of signal, that can disturb your signals. Okay. So this particular imperfection, the signal is not perfect at the receiver end. So this imperfection called signal impairment. This means if the signal at the beginning of the medium is not at the exactly same at the end of medium, like what I am saying and what you are listening. If you are listening exactly same what I am saying, that it's okay. But if I am saying something and you are listening some different thing, due to some noise has been added to my voice and you are listening something else, or you are not able to understand what I am saying. So it means this is signal impairment. Okay. So these three are the causes of impairment: attenuation, distortion and noise. So we will discuss these in the next lecture. Okay. So thank you.